Hello. Thank you all for joining us for this webinar on machine learning. This is an introduction to the machine learning reading for CFA program level 2. My name is Larry Tao. I'm Senior Director of Industry Research at CFA Institute. Before I begin, I'd like to cover some basic housekeeping issues. At the bottom of your screen, you can submit questions throughout the webinar. You will not see your question once it is submitted. We will do our best to answer as many questions as possible at the end of our presentation. If you have any technical difficulties, please click on the Help widget that has a question mark icon. It is my pleasure to introduce our guest speaker today, Mark Ainsworth, Head of Data, Insight, and Analytics Investment at Schroders. Mark has a degree in experimental psychology from Oxford University and a master's in operations research from Southampton University. He has spent his career at various industries and different organizations working in data analytics. So today we will present, Mark will present the machine learning reading in about 40 minutes, and we'll keep the last 20 minutes for Q&A. Without further ado, let me present to you Mark Ainsworth. Mark?
Hi, hello everyone. Thank you, Larry. So I'm going to be talking through the content of the CFA machine learning program over the next 40 minutes. And to use that, I'll be using some images taken from the reading. But before I get into that, let me tell you a little bit more about my experience with machine learning. So everyone is very aware that machine learning is a very big topic at the moment. And my first experience with that sort of thing was in my degree. So the modern machine learning techniques that are in the news, able to recognize objects and things like that, are often deep learning. They're neural networks, and they're very directly inspired from the way the brain works. So I first learned about these things in my degree 25 years ago. And throughout the rest of my career, which has been at a number of different places you can see on the screen, I've been using machine learning methods and mathematical methods to help people make decisions. Particularly interesting experiences were using various tools to help people make decisions about pit stop strategy, when to do pit stops during Formula One races when I was at McLaren. When I was at Tesco, the grocery chain, I was using machine learning methods to make predictions about how successful certain stores would be if they were built in particular locations, or predicting customer behavior. And when I was at Telefonica, they were using machine learning to predict user behavior and understand the movement of crowds. So through all that, my career has been about helping people make decisions using data and using analytics. I joined Schroders 5 years ago to set up a new team, which is called the Data Insights Unit. And we are a team of 20 data scientists, and we help the analysts and the fund managers in Schroders make better decisions about investments in fundamental stocks, in portfolio construction, using a number of data science techniques, and machine learning is one of them. And the CFA invited me to be a contributor to the content on machine learning. So I'm one of the people who was a reviewer of the CFA material. So let me start. Everything you'll see is essentially a screenshot from part of the CFA training material. The full detail is in the actual reading, but I've taken a few key points to draw out the points. This is useful to just clarify what it is we'll be covering. So the key topics covered by the CFA reading are, first of all, to distinguish between different kinds of machine learning technique. So I will be talking through that, but the key ones are between supervised and unsupervised machine learning, and we also talk about deep learning. Another topic which is very important, item B on this list, is overfitting and methods of identifying it, addressing it. So this is a really important challenge in machine learning, how to learn the data, learn the patterns of the data in a way that is useful and not too detailed. So I'll talk more about that. We then talk about some specific machine learning algorithms. Machine learning is not just one thing. It's lots and lots of different algorithms, lots of different ways of learning the pattern in some data. And so we'll talk about some specific ones, including penalized regression, support vector machines, k-nearest neighbors, ensemble learning, including random forests. We'll also describe item D, unsupervised machine learning algorithms, including principal components and k-means clustering. These are both ways of simplifying data. And finally, we will touch on neural networks and deep learning, the kinds of things that are much more in the news recently. So to start, I just want to describe what is machine learning. I think the headline I say here is the key idea. We're distilling the pattern in some data. Distilling the pattern in data. So this diagram shows the process of using machine learning, and I hope many of you will be already familiar with regression, linear regression, and it has a very similar quality. Regression is in many ways another kind of machine learning, but there are lots of other kinds. So first of all, looking at the top left here, you have the same sort of inputs you have for regression. You have some outputs, y, which in regression would be referred to as the dependent variable, and in the world of machine learning that's referred to as the target. And then you have many inputs, many independent variables in regression. They're referred to as features in machine learning. And you start with labeled data. So you have all this data, you've got all the outputs, you've got the inputs, and you have many of those, and that's your training data. You then feed that data to the machine learning algorithm. In this particular case, we're talking about supervised. You feed it to the machine learning algorithm, and the end result of that is a prediction, a rule about predicting what y would be given all the different values of x. Another very important part of using machine learning is to test the performance of that model. So here we show this. You also hold back some test data, which has the same characteristics. It has a target that you're predicting, has features that you use to make that prediction, and you feed those values in and evaluate whether the model performed well. A very important feature there is that you're using different sets of data, but taken from the same source. There's a sense in which any machine learning algorithm, it is learning the data that it was shown. It's learning the data it was shown, and it's learning the detail, and it's learning the more general patterns. And we need to test that it has learnt, hasn't learnt detail that is sort of distracting, it's learnt enduring patterns. As I said before, machine learning is not just one thing, it's lots of different algorithms. So this table summarizes all the kinds of machine learning algorithm that the reading talks about. In fact, there are dozens of others as well, but these are the ones that give you a sense of the key ones. So some of the things that vary are whether it's supervised or unsupervised. All that means is, do we have a known thing we're predicting or not? So if we don't have something we know we're predicting, really the algorithm is just sort of simplifying the data. But if there's a target variable, then we're making a very specific prediction. What will the outperformance be? What will the category be? And then another important split is between whether the values, the predictions, are continuous or categorical. So a continuous prediction might be how much will this stock outperform its benchmark between now and 6 months. Categorical might be, will the stock outperform the benchmark or not? or it might be, is this company classified as a polluting company or not, given text descriptions. And there are some techniques that can be used for both. So there are different techniques suited to different sorts of problems. I mentioned before that one of the key problems is referred to as overfitting. This is known as the generalization challenge. So this diagram tries to show the nature of this problem. The points, the circles and the triangles on this diagram, show the data we're training, we're trying to learn. We're trying to get the algorithm to learn this data. And on the left-hand side, you see the algorithm has done a bad job of learning the patterns of that data. It's drawn a line, but it's drawn it, not in a good place. That's something that can happen if your model is too simple. On the middle option is a model that is overfit. So it has got a complex curve that splits this area into two sections, and it's perfectly split the triangles from the circles. The problem is that describes the data that is seen, but that may be more complex and more detailed than would be true when you take other examples in the future. The history you've seen doesn't perfectly describe everything that will happen in the future. And on the right-hand side is a good fit. This is a model that has done a pretty good job of splitting between the circles and the triangles, but it hasn't become too complex and hasn't learned unnecessary details that probably don't apply in the future. The terms that are used in the machine learning world for these sorts of errors are bias error, variance error, and base error. So base error, the third one, is in a sense one of the reasons why this is such a problem. There's always noise in the data. There's always random variations. And so one of the things that means is that not everything that you see is important. Some of it is distraction. You then have two other sorts of error. Bias error is the kind of thing that happens with the underfit case, where you just haven't captured the pattern correctly. You've got the wrong sort of shape. And variance error is where the model has picked up, has been distracted by the variations, has become too detailed and, as it were, remembered the detail of what it was shown, but those details don't apply for future cases. So those make models that are unstable. And the next page here shows an important trade-off that exists. So you have, on the x-axis here, model complexity. So on the left-hand side, a very simple model, perhaps just one variable, like a very simple linear regression that fits a straight line. And as a model gets more complex, it has more variables, it has nonlinear relationships. It might have hundreds or thousands or millions of parameters that allow it to learn very complex patterns. You can see that the bias error, the dashed line, goes down. The more complex a model is, the better it is able to learn the patterns that it sees. But the variance error goes up. So the more data that the more complex a model gets, the more it learns everything, not just the patterns that matter, but also the patterns that are noise. And so the more complex the model gets, the variance error goes up, and you have, it learns details that are irrelevant. And the optimum is somewhere in the middle. And this is a key technique that needs to be used in machine learning, is to find the balance where the model has learned just enough pattern, but it is useful without getting distracted by the noise. The particular techniques that are used for this are something that I suggest you do further reading on, but there are a number of different techniques to find that balance. The key one is to hold back a test data. So you train your data on you train your model on one set of data, and you hold back a sample from the same source. So, for example, if you're training a model to predict whether a stock would outperform the benchmark, you might train your data on all the share price moves from 2010 to 2016. You would train your model on that, and then you would, having trained that model, you would then evaluate the model on 2017 and 2018. So it hasn't seen the details, and what that very quickly reveals is the right balance, and you can try that with lots of different levels of complexity. So you can try building lots of different models at different positions in this x-axis, and what you'll find is that when you try making that prediction on 2016, 2017 on very simple models, it's not a good model because it just doesn't learn the patterns. And if you give it very complex models, it doesn't do very well because it's distracted by the noise, by the events that happen to happen. And you find the balance. And then finally, you've done all that work, you can then evaluate it on 2018, 2019, and you know exactly how well that model is performing. So this is a really important part of how a machine learning practitioner finds a good model. One of the first kinds of models that is useful for anyone to use is called Lasso, which stands for Least Absolute Shrinkage and Selection Operator. And this is just a particular approach to solving that problem of balancing the complexity of a model. So if I hope you're familiar with regression, but just to remind you what this is showing, this is on the left-hand side, we have the sum over n, over all of our observations of the model, y hat, and the difference from the model to the actual observations, y. And we square that, so that's the error of the model. And you would, when you're fitting a model, you're minimizing that error. So fitting a normal regression model consists of just minimizing the left-hand side, left-hand sum there. But if you had 100 variables, this is a very complex model, the risk is that you might go to the right-hand side of that previous chart, and you'll have a model that has learned every detail, whether it's noise or signal. So the right-hand side of this equation shows the letter B hat is the part that describes the actual features of the model. It describes the parameters of the model. And what this part does is, when you minimize the whole of what you see here, it's trying to minimize the errors on the left-hand side, but it's also minimizing the parameters. So effectively, the effect of using this part of the equation is your optimization tries to remove some of the models, and it makes the parameters smaller. So by changing the lambda symbol here, you're changing the strength of that sort of penalty. So it's a penalty against complexity. By controlling that parameter, you can control where we are on this left to right scale on this chart. With a very high lambda, you have a simple model on the left-hand side. On a very low lambda, you have a complex model. So this is a tool used to make the balance between learning the detail, learning the sort of fine detail, and learning the big patterns. So it's a very common method used in machine learning, and there are other related ones. A more unusual kind of model that feels less familiar to somebody who knows linear regression would be support vector machines. This is an exotic sounding term, but this is actually quite a simple idea. These are used for classifying into groups. So for example, classifying whether a stock would go up or down against benchmark using various pieces of information fed into it. And in this example, we've just got two variables. And let's imagine that the X's were cases where the stock went up, and the triangles were the cases where the stock goes down. And the algorithm involves finding lines that split into these two groups. And the support vector is just the word given to this, this sort of boundary area, which is defined by where it touches the items highlighted in a circle. Now this seems like quite a simple idea, but what's really powerful about this is this can be done not just in 2 dimensions, but hundreds of dimensions. So it's splitting the data into with a line or a plane or a hyperplane across hundreds of variables, And these can be combined in all sorts of very powerful ways. There are a number of modifications to this that also allow more complex, subtle ways of doing this. I know that Bloomberg have a very powerful machine learning algorithm that classifies news into topics. It kind of identifies, is this news item about a particular company? Is it about a particular subject? Is it about an earthquake, or corporate news about a director? And it takes as its inputs the words and the phrases in those articles, and then it uses this technique, support vector machine, to slice these sort of 100-dimensional spaces into little sections, and then it essentially gives a prediction of classifying what each article is about very quickly. Another kind of example that's quite easy to understand is called K nearest neighbor. So this is a very simple to implement, but it performs less well on very large data sets because it's very computationally intensive. So K nearest neighbor is very simple. Let's suppose we have that same sort of data we had before. So we have the observations of two features, X and Y, and the prediction is, will the new observation be an X or a cross or a triangle? And here we have this new observation, the diamond, and we need to say, do we think this will be classified as a triangle or a cross? And we simply expand a circle from that observation and pick up neighbors. So it's the nearest neighbors, and a key decision is how many neighbors. K is the number of neighbors. So on the left-hand side, you can see with one neighbor, you just find which is the most similar other observation. And in this case, it's that triangle just to the below left of it. And so on the basis of that, you would make the prediction that this one will also be a triangle. On the right-hand side, you can see we have a K of 5, and here it's picked up 3 triangles and 2 crosses. And so now you would say, okay, we think there is a 60% probability, because there's 3 out of 5, 60% probability that this observation would be a triangle. And so this is very simple to understand. We use this technique extensively back when I was in Tesco, making predictions about how well will a store perform. We would find the most similar other stores and simply use them as a reference point. And what's very powerful about that, you can then average those similar cases and make your prediction. What's really very effective about that is that it's very understandable. You can say, let's say we're making a prediction about whether a company will outperform or not. The most similar other cases are Apple in 2012 and Nokia in 2007. And this suddenly becomes very easy to understand for people. Another very popular kind of machine learning is called a decision tree, sometimes known as CART, classification and regression tree. So a decision tree operates by a sequence of steps which take the data and chop them up, split them by decisions. So here's an example where we have 2 kinds of variables, investment opportunities growth and free cash flow growth as the features. And it, first of all, splits by the investment opportunities based on a particular threshold, here 10%, yes or no, and then it subdivides and subdivides. And it uses a method to identify at each step which is the most useful variable to split things by, and which is the best place to do that split. This slide here just illustrates what that looks like. Again, you've seen a few cases where we're trying to make a prediction based on the place in a 2-dimensional grid. Here you can see this is a more complex pattern. You've got lots of minor dashes in the middle and some pluses on the left and the pluses on the top right. And so the decision tree has essentially split this space, first of all, in that x dimension at plus or minus 10%, and then further subdivisions in other parts. So this is the end effect of what a decision tree is doing, as it's creating these sort of rectangles in space. And again, decision trees need not just be in 2 dimensions, it could be hundreds of variables that are used. A very common refinement of this is random forests. So decision trees have been a machine learning method that has been used since the 1980s, often used for credit scoring. Random forest is a new version, and this has become more popular as computers have become more powerful. The idea with a random forest is you train lots of models. This is what's referred to as an ensemble method. It's a collection of models. And so here, we've got the same data, and we've used it to create many different trees. And you might wonder, well, how if you give it the same data, why does it have a different tree? So the particular method used is to create subsets of the data. You would, for the first tree, you would only use, say, 2/3 of the data and only 2/3 of the features. So you sort of remove some of the data, and you would do that randomly. And then on the next tree, you would do it again, but with a different random selection of observations and a different random selection of features. So no one tree sees all the data, but every variable, every data point, and every feature is in some of the trees. So it reflects the fact that if you're training a model on history, if you're training your model on stock prices from 2010 to 2018, well, the truth is you're making a prediction about 2020, and if you could have used 1999, there's a sort of there's various data you don't use, so it's useful to have each tree miss some stuff. And then what you do, you combine these models, and they vote. So usually you would have a tree that's predicting will the price go up or down, and pass your new observation to all of those trees, and they vote. Whichever outcome has the most votes, that is your prediction. Random forests are very popular for 2 reasons. One is that they're often very robust. They're good at not learning too much detail because they have this feature that some of the data is dropped from all the trees. A second feature is that they are good at making a probability prediction. So if it said there's a 60% probability that this stock will outperform because 60% of the trees have made that prediction, that's a very useful feature. And generally speaking, they're found to work very well. So in my team, we've built several random forest models that are used to predict bond issuances or IPOs. So we would take as features the various different characteristics of the bond, how much interest there is, how much money there is, what sector it is in. Those are the various features, and then it would predict how successful it will be. Those were all examples of supervised learning where we're making a prediction. Often in those examples, it was what symbol it would be on the chart. There's a whole other area which is very popular called unsupervised learning. And this is about simply simplifying the patterns of data. You have this very complex data, how do we simplify it and help people understand it? Or sometimes these methods are very useful to simplify the data before feeding it into machine learning. I described earlier how if machine learning learns all the features of the data, and if you feed in lots of very complex, messy, noisy data, it will learn it if we're not careful. So this is a way of simplifying the complexity. So one technique that's been very popular for many, many decades, and quants have been using this method for a very long time, is principal components analysis, PCA. So this is a dimension reduction technique. This uses all sorts of fundamental linear algebra methods, and essentially this visual tries to illustrate this. You have 3 dimensions of data here, X, Y, and Z. Let's suppose they were 3 different durations on the yield curve, and yield curves can have lots of different very complex shapes, but you want to sort of simplify it. So here we've got these 3 dimensions, and each of these dots would be at different times the different values for the shape of the yield curve. And essentially PCA simply finds the main sources of variation in that. So in this case, PC1, principal component 1, it's found the main thing that seems to vary across this data, which is some combination of X and Y and Z. And then what's left is the next principal component is something that is at 90 degrees to that. And what you now have is a two-dimensional summary of most of the variation in the data. So you're reducing the number of dimensions from the features. So you take a 3-feature data set down to 2 features, which are a blend of those things. So principal components analysis is reducing the number of features. Clustering is reducing the number of observations, or summarizing those observations. So the idea of clustering is simply you have all these observations, here's all these points. Note that they're all triangles in this example, so there's nothing we're predicting, we're just trying to capture the pattern. And as you can clearly see, these form some clusters. There's clearly some form close to others. On the left-hand side, that's not a good clustering. The middle option, that's a pretty good clustering. The right-hand side, it's maybe a better clustering, but of course it's become more complex as well. It may be useful, or it may be too complex. So there are some choices to make about how detailed to make your clusters. A very, very popular method for clustering data is called K-means. And one of the reasons it's popular is that it's a very efficient method, and it generally works very, very well on all sorts of data. But you have to make the decision, how many clusters will I have? So here's some example data, and we're going to make the decision we want to find 3 clusters. And how it works is you basically randomly place a centroid, a kind of center point for each of these 3 clusters. So here in the top left diagram, step 1, it's just got 3 randomly selected places. Step 2 then shows how, because of those positions, those lines now define for each position in this space, which cluster each place would fall into. You then find the mean, the center of those points based on those spaces, and that moves the center to the data. And you just keep iteratively doing that. So it's a very simple to implement method, and it gradually finds the centers of the clusters. So you can see by the time of step 6, it's naturally found these points. They started off in random positions. They've moved towards positions essentially in the middle of those clusters. A key question is how many clusters you have, and usually what you would do is you would try a number of different solutions. You might try 2 clusters, you might try 4, and inspect the results and see how well those clusters have worked. So in my team, we used this sort of method to cluster stocks in our emerging market equities portfolio based on the similarity of their price moves. So in these examples, you can see 2 dimensions. We used the 200 dimensions of the last 200 days of the share price moves. And we were essentially using that to create, it was about 25 clusters, which has the effect that all the companies that move, where their share prices move in a similar way, fall into the same cluster. So that became a useful tool to use as part of risk management and looking at the performance of the portfolio. Hierarchical clustering is another method, and rather than starting with a defined number of clusters, it simply summarizes the way, either starts by combining together very similar points or chopping them apart, but the end result is this hierarchy. So here on the left-hand side, you can see some example observations, and on the right-hand side, what's known as a dendrogram. So this is a visual that summarizes this hierarchy of clusters. So you can see in this diagram, it says, where it says 2, this is one of the most similar pairs of points. C and D are very close to each other. And you can also see A and B are closely linked. They're close to each other. So first of all, it's found the very close pairs. And if you were to draw a line on this diagram, you can have different sorts of numbers of clusters based on how similar they are. So it sort of it groups the items together, and then it groups the clusters together. So if you were to say, I want just 2 clusters, you would draw the line at that upper dashed line, and essentially you'd have a group that has G, H, I, J, and K, this sort of group in the top right. If you wanted to split it into 4 or 6 clusters, then you would draw it at that dot dashed line, and then you'd have a different solution. So it doesn't require you to know the number of clusters in advance. Finally, I'll just touch on the subject of artificial neural networks. So you hopefully will be familiar with logistic regression. Logistic regression is just linear regression, but where the data is transformed with a logistic curve, an S-shaped curve. And you could visualize that with the diagram on the left. You're taking a set of inputs, you have some weight applied to them, and they are summed to an output. And by applying that sort of S shape, everything stays controlled. And in a neural network, you simply have extra layers of points. You have these sort of hidden layers. So in this right-hand diagram, Z1, Z2, Z3. This starts to make a very complex model. So every single line in this diagram needs a parameter, needs a weight. So where on the left-hand side we have a not complex model with 4 parameters, on this right-hand side we immediately have already on these 1, 2, 3, you can see lots of parameters. The model that Google trained to beat the best human at the game of Go had millions, literally millions of parameters. It had many layers. I think it was 4 layers of sort of these hidden nodes, and it took extraordinary amount of compute time to calculate, and it was trained on 40 million games of Go. So it is perfectly reasonable to have a very complex model, but you need a lot of data to train it. So in situations where you have a huge amount of data, deep learning and artificial neural networks can be very powerful. I guess the key idea is the more complex a model, the more complex the patterns it can learn. So if it's learning how to play the game of Go, if computers are learning how to recognize stop signs on roads, so these techniques are very powerful in machine vision, then that complexity is useful. In the most sophisticated models, there are many layers of, not just one layer, but lots of layers, and this allows these models to learn abstractions and very complex, sophisticated patterns. But again, you need very complex, sophisticated data. You need millions and millions of observations to really train those models well. So in my team, we've done some experiments of using deep learning, but to be honest, it's not often we've had enough data to train those models effectively. So these can be very powerful. I think a great example I saw of using neural networks was Thomson Reuters, Refinitiv. They had a neural network deep learning model that took the text description of a legal proceeding, so sort of a summary of a court case, and they trained that model to summarize it in a sentence or 2. And because Thomson Reuters had literally millions of these court cases, because they've been summarizing those globally over many decades, they were able to train the model to basically create a written summary of the court case. And this performed so well that you actually couldn't tell the difference between summaries written by people and summaries written by the computer. So when you have enough data and it's complex enough, you can do some extraordinarily powerful things with these. It's not that often that there's opportunities to do that with financial data. In finance, in my experience, usually you have tens of thousands of observations. Neural networks are very powerful when you have millions of observations. And I think a key downside of neural networks is they're so complex, they're hard to explain. So it's very hard to understand what's going on. You can't look at all those parameters and make sense of what's happening. So that was a very quick run through the kinds of content that the CFA reading talks about. that reading has a lot more detail than I was able to cover, but I hope that gives you all a flavor of some of the things we think about in use of machine learning.
Wonderful. Thank you, Mark, for that very succinct presentation. I think this is a very new but also fascinating subject for our members. Given that we're all mostly finance professionals with not very much technical background, I thought I'd ask you to do maybe a 2-minute quick summary before we ask the questions from the audience.
Sure. So machine learning is just a collection of algorithms that have been devised in the computer science world for distilling the pattern in some data. And an important part of that is distilling the pattern that is useful and discarding the noise in that data. So that is referred to as the generalization problem. And some of those algorithms are focused on distilling the pattern of how to make a prediction, whether that's whether a category or a specific value. And some of those algorithms are distilling the pattern to simply describe the data, to simplify it, whether that's clustering or simplifying the variables. And often these methods can be useful in lots of places in finance, and there's obvious ones like predicting the path of share prices. There's much less obvious ones about classifying companies' ESG exposures based on written language. There's all sorts of things like that, but that's the essence of it.
Great, thanks a lot, Mark. So we'll get into the Q&A, and we do invite the audience to continue to submit your questions, and we'll work them into the queue. So we'll start from the beginning. What is the background? What are the prerequisites that are required for someone from a finance background to start learning machine learning?
So it varies actually. So there are, I would say, some experience in programming, in using modern coding languages like Python or R is really very useful, because most of actually building a machine learning model and understanding what it's doing, certainly in my team, we do that by writing code and using those sort of coding languages to inspect that. Having said that, increasingly there are commercial products that are being sold which kind of package up the problem for you and let you create models in a much more sort of point-and-click way without knowing a great deal of detail. For example, there's a tool called Data Robot, which you can load some data in, press a button, and it will automatically try 100 different machine learning models and give you an answer. However, if you want to actually understand what's going on, I think you need to learn to code. You need to know, have a certain knowledge of mathematics and linear algebra to be able to really understand what's going on. But I think the intent with this is, even if you don't actually do it, to know that some of the issues that apply. And I think if I were just to repeat this point, this problem of overfitting is the most important one I think everyone needs to understand. These methods learn the pattern of some data. If you're not careful, they'll learn the noise. They'll learn the features that happened to be true last year, whether they will happen next year or not. So it's really important to learn the pattern that is the signal, and not to learn the noise. But the best way of getting sort of stuck into it is there's some really good kind of courses, but generally you need to learn to code to sort of really get stuck into it.
Wonderful. So coding and linear algebra, those are the key prerequisites, it sounds like.
Yeah.
The next question is, how do you think machine learning will impact the future of investing? So it's a very broad question. I think we can, if you can comment on what are some of the areas do you think we'll see more applications?
So there's a really good little rule of thumb, and there's a very well-known researcher in the field of machine learning called Andrew Ng, and he said, if there's something that a person can do in 1 second thought, then it can probably be automated with machine learning. I think perhaps another way of putting it is if you could train an 8-year-old child to do something, then you could get machine learning to do it. So, for example, and this is all about learning patterns. So if you can do something in a second, it's because you've learned the pattern, whether that's recognizing a word or an object, or sensing the mood of the market. As part of our jobs, we recognize patterns, and once we've recognized them, we can act. Playing the game of Go, if you have expert chess players or Go players have a feel for what's a good next move. And so any part of the investment process that is pattern recognition will be automated and by machine learning. Truth is, most trading these days is already automated. Most trading is completely algorithmic, and that is because most of what makes for successful trading over short time periods is pattern recognition. And what's changed is these very powerful techniques mean that we can learn very complex patterns, but if what you're doing is based on understanding rather than patterns, so if you're trying to decide whether to invest in Apple today, there's never been a company exactly like Apple is now in the past. There are similarities, but that's not quite the same as pattern recognition. If you're trying to think about whether to invest in Apple, that depends on understanding in a much more general knowledge sense all the forces at work in the world, in the economy, in markets. So my belief is that fundamental investing will never be replaced by machine learning, but any part of the process, whether that's reconciling client records in the back office or kind of executing trades at the trade desk, if it feels like pattern recognition, it can be automated. And often there are parts of the process that feel like that. So a good example we had was one of the teams in Schroders needed to classify every company in the investment universe based on whether they burn thermal coal as part of creating an ESG screened product. And we didn't have that identifier in the database. So what they did, they trained a machine learning model to create that flag, that identifier, based on the description of the company. Because it's a simple pattern recognition. You can read the description of the company from the report, and you can quickly tell, do they burn coal or not? So they trained the machine learning model to do that, and now the process of classifying a company based on whether they burn thermal coal has been automated, because it's really just complex pattern recognition.
Wonderful. Thank you, Mark. I think that's very helpful. There's another question about the decision tree of sort of how to apply machine learning or not to apply machine learning in an investment situation. The question is there a list of questions that you ask in finance and then decide, whether you use machine learning and if you do, what type of machine learning tool that you would use?
That's a really good question. So I think the things that are the ingredients for success with machine learning, I think there's a few key things. So one is there some pattern that can be learned that endures? So I think, and a really important question therefore is how stable is the situation that you're training on? I think markets are an interesting challenge there because the market behaved a certain way one year, it doesn't mean it will behave the same way the next year. So considering the stability of the situation is an important one. The amount of data is another one. Machine learning is most powerful when you have a lot of data. Linear regression is a perfectly good way of capturing the pattern in some data. Linear regression fails when the patterns are complex, where there are interactions, there are complex non-linearities. And so if it is important to find those non-linearities and those complex interactions, then machine learning is the tool you should use, but there needs to be enough data. If you only have 100 observations, actually the truth is there's just not enough data to learn complex patterns. If you try to use a complex method on such a small data set, you will learn the noise, you won't learn the signal. So there needs to be a lot of data. And I'd say those are the two key kind of conditions. I think another important feature is that all the important data is available electronically. So if there's some decision being made where some of the things that people think about in making that decision are in their head in discussion, they're not in a database, then actually it's unrealistic to do machine learning, or it may not succeed because you need to it needs to have all the key things that really make a difference available in the equation. So quite often we've struggled with that because a human can make a better decision than the algorithm because the human has access to more information. So you do need all the information that matters to be in the database. It needs to be available to be trained. That's an important question as well.
Wonderful. That's really helpful. I think the other question is in cases where there are limited amount of data, are there simple ways to actually generate data, right? Because how do you actually create more data sets? Or, for example, if you have only annual data for 20 years, would quarterly data and then monthly data and daily data, etc., do the trick? Will that help generate more data? Or you would actually you would imagine the patterns would be different if you use a high-level data and concrete data sets?
That's a really good question, yes. So sometimes that can be done, and sometimes not. So I think, for example, in machine vision, let's suppose you're training a neural network to recognize the difference between cats and dogs, and you had 100 pictures of cats and 100 pictures of dogs. The kind of technique that they use is to create variations of those pictures where it's the same picture but rotated or squeezed or squashed or cut off a bit, and that makes the algorithm robust to those variations. But it's still, if you now presented it with a new kind of cat or dog that's quite different from any of the ones that it was shown, it would still fail probably because it hasn't really got the variation that you're looking for. And it's the same really with annual data. If you're trying to, let's suppose you're using data to make a prediction about, let's say, what will happen to the share price over the next year, then if you took annual data and turned it into monthly data, the fundamental problem you'd have is that data is autocorrelated. So let's suppose you're saying, let's look at December 2016 data, the annual year ending December 2016, and making a prediction about what will happen between now and December 2017. If you then also looked at November 2016, predicting November 2017, most of the data is the same. It's actually the same year mostly. It's this, and what will happen between November 2017 and 16 is sort of mostly overlapping with the other. So although you have lots of observations, you don't really have lots of variation. So there's no way of cheating that, actually. It's really a fundamental assumption that most machine learning algorithms make is that every observation is independent. They're independent observations, and so every observation is completely new information. If you took annual data and chopped it into monthly, it's like rolling, kind of different rolling periods, they're not independent, they're overlapping. And the material for machine learning is variation. So you haven't really increased the variation, you've just sliced it up into smaller parts. So that doesn't really work generally.
That's really insightful. I think people are always also wondering machine learning, right? Oh, the benefit of machine learning over linear programming. So the benefit advantage is machine learning can present more sophisticated patterns to you. So is that the main advantage? And are there ways to measure the impact of that improvement?
Yes, so that's right. It's the complexity of the relationships that it can be learned. And the measure is simply, when you then use your model, does it perform better? So I'm afraid I don't have the name of the author to hand, but a colleague was telling me about a paper that he'd read where they had looked at factor models and using factor models to explain share price performance has a certain predictive power if they, instead of using simple linear factors like kind of classic Fama French, they used machine learning models. Those models were then able to perform much better when then applied as a sample. So the proof is always when you then use the model out of your training sample, does it perform better? And there are many situations where it can. I think it's not a finance example, but I would offer this as a really good sort of example for thinking about why nonlinearities and interactions are powerful. Imagine you were trying to predict how tall a person was based on their age and their gender and their birth weight. And this is a simple relationship everyone understands. Everyone grew up when they were a child, and because some people, of course, are taller than others as adults, and of course, children grow, but there's this sort of nonlinearity. There's a thing where children grow. There's a relationship with age which stops when people are about 15 years old. There's another thing that the boys in particular suddenly grow faster when they're teenagers. There's a relationship with birth weight that is different in childhood than it is in adulthood. And so you've got interactions. Boys grow faster than girls when they're teenagers. You've got a nonlinearity. There's a sort of, the link between age and height is different for children than for adults. And that's, you just wouldn't, if you try to do linear regression to predict somebody's height from age and birth weight and gender, it just wouldn't work, it would fail. So machine learning is the kind of technique that can pick up and make sense of those sorts of patterns. And those sorts of, so there's nothing very exotic about nonlinearities, but that just gives a sense of that sort of idea.
Wonderful, very, very helpful. I think we have two more questions and then we'll close. One of the questions is, do you see any danger from the market in a stress situation that comes from automated trading executed on a machine learning model? I think the background is when we think AI, I think they're more effective in situations where they've learned a pattern. If they see something new that hasn't happened before, will AI actually cause problems?
Yes, so I mean, it's very well known that that sort of thing can happen. So the quant heart attack, as it's known, which I think was August 2007, is a famous case of a time when lots of quant hedge funds had trained algorithms on the patterns that had previously worked. And those were simple algorithms, and lots of hedge funds had essentially learnt the same patterns, and they were all trading the same way. And then suddenly an unusual thing occurred, and suddenly all these models massively misbehaved. So in the space of a few days, lots of quant hedge funds lost a lot of money. And one response all those quant hedge funds took from that is to look for much more complex sources of data and use more varied algorithms. So it is absolutely the case that a model can fail when exposed to new data that is unlike the data it was trained on, and that's why the stability of the sort of the problem is one of the conditions for machine learning being successful. I think for the financial system as a whole, there's so many different machine learning algorithms, there's so many different data sources that I don't think that's anything like as big a risk as it was 10 years ago, when there was a much smaller number of data sources and a much smaller number of algorithms, which more often sort of overlap to each other.
Thank you. I think that's a great insight. Last question is if people in a specific area of the business, say people in private equity or people in the risk business, they would like to find out more about models and applications that are used in their particular area, can you recommend some sources?
Yeah, goodness, yes. I actually I can't. I recommend on the general subject outside of finance. There's a newsletter that I would recommend. It's called Data Elixir, and perhaps we can send a link around to that after. In finance, I think I would recommend finding local meetups. So in London, there's a group called the London Quant Group, and regularly talks done on those sorts of subjects. So I think in every city there's probably a community that exists where people come together with an interest in this and they share those experiences. So I'm afraid I only know that group in London, but the equivalents will be in every city, and I would find those groups and meet with them, because in practice most of the work that people do is very secretive. People are very secretive about this, so find those communities, and people are more comfortable presenting to a group of 50 people than publishing this sort of information.
Absolutely true. On that note, I would also mention that the CFA Institute Research Foundation will be publishing a collection of literatures about applications of AI and machine learning, etc., in investments. So that summary, that literature review, will be published shortly. So do please look out for that as well. So with that, I think thank you, Mark, very much for joining us today and walking us through this machine learning reading. And for everyone in the audience, well, thank you very much for joining us as well.
Thank you.
Yeah, take care.